Alright, so welcome back to part 5 of Physics of the Atom. And now we're going to look at the applications of radioisotopes. So we learned earlier what radioisotopes were. Right? So those are elements which decay easily. Okay, so they decay, they give off different types of radiation, namely what? Alpha, beta, and gamma. Correct. So now we're gonna look at their uses. Why were these things so? Why were these elements that gave off radioactivity? Why were they so important? And we're gonna investigate that using this. So we're gonna first talk about radioactive decay. First of all, radioactive decay is a random process, okay? Because a very large number of identical nuclei are involved. For an effective model of the decay process, all of the particles involved, they need to be identical so that they have the same chance of decaying. Now, we all know that radioactivity is potentially dangerous, right? However, they are used in medicinal fields and in archaeology and many other things. So here are some uses. The first one we're going to explore is the use of radioisotopes in the medical field via medical tracers. Now, the compounds containing radioisotopes can be used as tracers inside of the patient. It is here, it is injected into the body and it moves through the bloodstream and gathers into the targeted organ. The tracer then emits gamma radiation, which is then detected outside of the body using a gamma camera. A computer then produces images from the information gathered, and problems such as blockages in blood vessels can be identified. What is the most common tracer used in the diagnostic medicine is Tritium-99m. The isotope decays by releasing gamma radiation, which is easily detectable by gamma cameras. And because of its very short half-life, it doesn't stay inside of the patient very long. That's a good thing in terms of how long it lives inside of the patient or exists inside of the patient, because you really don't want something that gives off gamma radiation to stay inside of the patient for, let's say, 10 years, because then you won't have a patient. Right? You won't have a patient. So that's what it means by half-life. How long does it live for? How long does it exist for inside of the organism? Right? Now, it's also used in radiotherapy. Radiotherapy could include chemotherapy, could include x-rays, many things. So radioactive emission can be highly ionizing and can cause cancers. So the very thing that we're trying to get rid of, it can cause. However, cancer cells are more susceptible to being damaged or being killed off by gamma rays than normal cells are. By gamma radiation, the sad part is that sometimes normal cells do die because there's only so much your normal cells can take on. Now, during radiotherapy, a high intensity beam of gamma radiation is directed at the tumor, right? And as you can see, even though it's directed at the tumor, it can affect every cell inside of that body. The cancer cells will receive a very high dose of radiation and hopefully die off. The key word here being hopefully die off. The gamma ray may be produced by cobalt-60. Now, that's the thing. That's what happens with cancer patients. Yes, I mean, they get chemotherapy, but then you would hear, oh, the person gets sicker after chemotherapy, and that's the reason why they appear or get sicker after chemotherapy, because the gamma radiation would have affected all of the normal cells while they were under chemotherapy. So not only did the cancer cells get attacked by the gamma radiation, so did the normal cells, and this will cause the normal cells to die off. And sometimes this may cause a new cancer to form depending on the host, right? Remember, different strokes for different folks, and I mean that the way our bodies handle diseases are different across the board. Because remember, some people might have a very high immunity to something, while others might have a very low immunity. It depends on the person's genetic makeup, right? So that is the reason why some people come out of chemotherapy sicker than how they went in. Some, known fact, some people who have experienced chemotherapy do not lose their hair, they do not get sick. Yes, that's exactly it. Different strokes for different folks, people respond differently to medication. People's bodies respond differently. Now here's another application of radioisotopes, and it's used in dating fossils, right? So we call that radiocarbon dating. And the reason why it's called carbon dating is because scientists use the fact that there are different nuclides of carbon, one being more abundant than the other. So in this case, we're going to focus on carbon-12 and carbon-14. Now, all organisms contain carbon atoms, right? The major atoms, the main atoms in organic organisms would be carbon, usually oxygen, and hydrogen. Those are the main ones, right? So the carbon atoms are absorbed from the atmosphere during its lifetime. For instance, human beings, we inhale oxygen and we give off carbon dioxide. And do note that the atmosphere, we inhale all the gases. The air that we inhale consists of all the gases you could think of: carbon dioxide, hydrogen, helium, neon, argon, chlorine, fluorine, all these gases that we are aware of. However, our body is so intricately designed based on specifics. I don't even know how to say the word. Specificity. Let's say specificity. But you know what I'm saying. Based on specifications, right? Our body's hemoglobin, the hemoglobin that flows in our blood, binds nicely to oxygen, even better to carbon dioxide. But those are the two gases that keeps us going. We inhale oxygen, we inhale all the gas, but our body is bound to oxygen to replenish our organs, whereas the blood, which acts as a bus, comes right back up and gives off the carbon dioxide during respiration. Okay, so even plants do it. Plants take in oxygen and give off carbon dioxide, right? Sorry, take in carbon dioxide, they do the opposite. They're taking carbon dioxide and give off oxygen, right? So that's what plants do. And that's why plants are so important to the environment, because they act as recyclers of the air. So all organisms contain carbon atoms absorbed from the atmosphere during its lifetime. Most of the carbon absorbed is carbon-12, which is a stable isotope, but a small portion is carbon-14, which is a better emitter. When carbon-14 decays, it forms a stable isotope known as nitrogen-14, and that is the equation right there. So you can see that once the beta radiation comes off, we have an increase in the proton count, right? So it emits an electron that wasn't there before, and the proton count therefore increases. However, the mass number stays the same. The proportions of carbon-12 and carbon-14 in the atmosphere are constant as new carbon-14 is produced by interaction with cosmic rays at the same rate carbon-14 decays. This means that all living organisms maintain a constant ratio of carbon-14 to carbon-12. Once the organism dies, there's no more carbon. There's no new carbon, right? You cannot take in any new carbon. So the carbon-12 nuclei, which are stable, does not break down. However, guess what breaks down? Carbon-14, right? So it decreases over time, and we call this a half-life, which we're going to lead up to just now. So scientists can measure the ratio of the two isotopes by measuring the activity of a sample of carbon taken from biological remains. The ratio can then be used to find out how long ago organisms died. So we know that carbon-14 has a half-life of 5,700 years. That's how long it takes to break down, right? So the remains of an organism which died 5,700 years ago would have half as much carbon-14 as an organism that died today. Okay? So it takes 5,700 years for carbon-14 to decrease by half. The half-life of a radioisotope is the time taken for the mass or activity of a given sample of it to decay to half of its value. So say you had 100 carbon-14s, it would take 5,700 years to decrease to 50 carbon-14s. That's what it's saying. So the half-life of a radioactive material is not affected by conditions external to the nucleus. And this includes physical conditions such as temperature and pressure, chemical conditions such as whether or not the isotope is in its pure state or chemically combined with some other element in the compound. Radioactive decay is exponential with time, as can be seen here with the graph. And every single experiment you execute to represent radioactive decay would produce a decay curve that looks exactly like this. However, the half-lives would be different. Right? The half-life would be different. So, depending on the material you're using. Okay? So let's look at this. So the half-life is what you measure in between here. So this is the half-life in between here. So, sorry. So let me look for the, so this is a half-life in between here. So the half-life, so say we had 100 things here. The half-life would then be taken at 50, because remember, it's always the time it takes to half the amount to break down. So this will be the first half-life, and that will be the distance between here and here. That's the first half-life. So this is 10, right? And this, let's say this is 20, 30. It's not necessarily going to get the same numbers all the time. So then you want the second half-life. The second half-life would occur at half of 50. So half of 50 would be 25. And this would be the second half-life right between here. Sorry. The second half-life would be between here. Sorry. Okay, so this will be your time taken right between here, from the first half-life to the second half-life. So this will be the distance right here. So let me highlight that. So this will be your first half-life, and between here will be your second half-life from the first. And guess what would be your third? Your third would be a half of 25, which would be what? 12.5. And we're talking about these points right here. Right? And so your third half-life would be right between here. So you measure the distances between here. So you know that this is 10. So it could be 10 days, 10 throws. This would be 10 as well, because this is 20 minus 10 will give us 10. 10 whatevers. And this also will be 10. But it's not all the time that is equal, right? So let's look at something else. Something started, let's say this is approximately 1600, just for the sake of calculating easily. Half of 1600 will be 800. And of course you would use a ruler for this. And this will be your first half-life. What is a half of 800? Yes, half of 800 is 400. So you will go across here and down. And this will be your second half-life. So your first half-life is approximately 20 days. Of course, let's say about 22 days. And your second half-life would be, this is 10 in between here. 40 minus 30 is 10. And then since this is 2 from 10, so we could say 8. This is 8 right here. So that would be 18 days. So you see, it's not always the same, so you're going to have to find an approximation. And half of 400 is 200, right? That will go across. And remember, I'm not using a ruler. This is just all freehand. So this will be your third half-life. And your third half-life looks like about, wish I had a ruler. Let's say, let me do it properly so it could look a little better. Okay, so let's say it went right across to little point right here. Okay, so looking like it. So our third half-life would be about how many? Right. Our third half-life will be 10. So it looks like about 20 days. Right, so then we'll find the average half-life, which will be 22 plus 18 plus 20, and that will give us 60, right? 60 days. And to find the average, divide by 3. 3 into 60 gives 20 days. So our average half-life is 20 days, right? For this particular, whatever it is, material. Now we are on to comprehension. So we're going to say now, why would an alpha particle emitter not be suitable for use as a medical tracer? That's because it has, it doesn't penetrate materials well, right? It's not as strong. It doesn't penetrate materials well. Or the radiation is not really strong. Right? Okay, a sample of wood taken from an arrow is found by radiocarbon dating to have an activity 1/8 of that for a modern piece of the same type of wood. Estimate the age of the arrow. So 1/8. So we're looking at how many half-lives. We're saying 1/2 times 1/2. That will give 1 quart. So 2 times 2 is 4. 4 times 2 is what? 8. So from this we see that we have 3 half-lives. So if you have 3 half-lives, you know, 1 half-life is 5,700, because we're talking about carbon, 5,700 years. Then we have second half-life, another 5,700 years for it to break down to a quart, and then it takes another 5,700 years to reach to 1/8. So in looking at it, we would say 5,700 times 3, and that will give us 15, 17, 17,100 years. Right? So that is how you work this out. Then it says an ancient piece of cotton cloth is found to have an activity due to carbon-14 decay 1/4 of that of a modern cotton sample. Estimate the age of the ancient piece of cloth. So we could say, we know that 1/2 times a half is equal to 1/4. So we therefore know from these two we are dealing with 2 half-lives transpiring. And since we're dealing with carbon, once you hear the word once you see carbon 14, you know they're dealing with carbon decay. So we know that carbon 14 takes approximately 5,700 years to decay to from half its original amount. So if we're dealing with 2 half-lives, we know that we're dealing with 2 sets of 5,700 years. So it took 5,700 years of carbon, 5,700 years had to transpire for carbon 14 to decay to 1 half-life, and then 5,700 years again for the carbon 14 to decay to a second half-life, giving 1 quart. So 5,700 times 2 will give 11,400 years. Okay? So I hope this helped, and see you around for part 6 of the release of nuclear energy.